Every time an engineering team adopts a new large language model, they hit an immediate bottleneck. To get that model to actually interact with their local environment, they have to write a custom API wrapper. As the ecosystem expands, this creates a mathematical failure point known in computer science as the M by N integration problem. This architecture illustrates the M by N problem. Connecting a growing number of models to external data sources generates an exponentially complex web of point-to-point connections. For tool providers, this means maintaining entirely incompatible plugins for every AI platform. For developers hosting AI applications, it means constantly rewriting integration logic just to keep their baseline features functioning when a new model drops. This tightly coupled, brittle architecture creates a significant barrier to scaling autonomous agents that require access to diverse, enterprise-grade data. The Model Context Protocol, or MCP, is an open-source standard built specifically to decouple language models from their underlying tooling. Inserting a standardized protocol layer collapses system complexity. Instead of M times N connections, we only need M plus N. AI hosts implement the client protocol once to speak to any system. Conversely, tool providers write one server implementation to instantly support all MCP-compliant models. This functions exactly like a hardware standard. Much like USB-C eliminated the need for dozens of proprietary charging cables, MCP provides a universal data interface. AI tooling is shifting out of isolated proprietary walled gardens and into a more interoperable ecosystem. To understand how this works in practice, we have to look at the internal mechanics. MCP operates on a strict client-server architecture. This diagram starts on the left with the host, the AI application capturing input. Inside lives the client, an adapter handling network communication. The client communicates across the boundary to the server, a lightweight wrapper executing the target capability. This handshake happens over a clearly defined transport layer, functioning locally via standard I/O streams or remotely over HTTP. This strict separation of concerns provides a security advantage. Models reason in isolated environments, while code execution happens in separate sandboxed server instances. MCP servers strictly categorize all capabilities into three primitives. First are tools. These are executable actions, like writing a database record. The AI model itself chooses when to invoke a tool. Because tools execute external state changes, they require a security protocol. The host application enforces a user approval gate, as shown in this UI prompt. The second primitive is resources. Unlike tools, resources are strictly read-only data retrievals with no side effects. Resources are mapped to specific URIs. Instead of the model spontaneously invoking them, the host application usually fetches them to build context for the LLM. The final primitive is prompts. These are predefined, user-controlled instruction templates hosted on the server, designed to guide the model's behavior before a task begins. Enforcing this three-pillar model forces developers to make explicit architectural choices about what an AI is allowed to do autonomously versus what requires human governance. From a developer's perspective, exposing a local database through MCP is a streamlined process. In this Python implementation, a standard SQLite backend query is converted into an MCP tool using one decorator line. The server automatically parses the docstring and type hints to map the tool schema, advertising its purpose to the AI client. By removing the need to write custom HTTP routing or manual model parsing logic, developers can wire existing databases straight into agentic workflows. Let's trace a single query through this architecture. It starts when the user submits a query to the host. The LLM evaluates its options and selects the required MCP tool. The client packages the payload, requests the tool call, and the server executes the action. The server returns structured data to the client, feeding it to the LLM's context window. The model then generates the final response. This exact sequence abstracts away the API complexity. The language model focuses on reasoning, while the protocol handles the raw mechanics of execution. The M by N integration bottleneck is addressed by replacing bespoke wrappers with a universal contract. As AI language models transition into background agents, standardized tool discovery provides the infrastructure for consistent local tool access. For forward-thinking system architects, implementing the Model Context Protocol is the crucial foundational step in building more interconnected AI systems.